Hello friends, I am Amir Nizami and today we are going to study the governing differential equations of a beam. So let's start. Here is a beam. So we have just cut a section. So it is a distributed load here and we have just cut a section of a length dx and we have shown here, you can see. So this load is distributed over the length dx and making a free body diagram. So just here the bending moment is m and at a distance dx it is m plus dm. Similarly the shear force v plus dv and here it is v. And now we will have the equilibrium equations with us. That summation of the forces along the vertical direction y is equals to 0 and we are taking the positive sign in the above direction. So just we are writing here v is the upper direction, so it is positive v, then it is minus of v minus dv, and this distributed load, if we have to just make it as a point load or a concentrated load, it would be qx into dx. So qx into dx, that should be equals to 0. So therefore this will get cancelled and this would be the q of x equals to minus dv by dx. So we can say that this distributed load is nothing but negative of the rate of change of the shear force. Now here we about this point O, we will just take the moments. So summation of the moments from the equilibrium equations, we can say that should be equals to 0 about point O. So therefore this is the moment m, this is m plus dm. Okay, so in anti-clockwise we have taken the positive, so therefore this would be the minus m for the clockwise direction. So minus m and then it would be plus m plus dm, and then this would give the moment and about point O in the clockwise direction. So therefore it will be the minus of q of x into dx. This would be the force multiplied by dx by 2, which would be acting at the centroid CG of that. So therefore the length would be dx by 2 from this point O. So therefore qx dx into dx by 2 minus of this load would be v into dx. So sorry, I think this point O is we have chosen the wrong direction. This should be chosen here at this point. Okay, so we should correct here that this point is over here at this position. So therefore the distance from v into this distance would be the dx. Okay, so v into dx, that should be equals to 0. So when we will just make this would get cancelled, dm minus and qx dx into dx by 2, where dx is a very small quantity. So the small quantity, we will, if square it, then it will be dx square. It would be higher, smaller. So we can just neglect it, or otherwise we can say in the limiting sense that limited, if we take the limit at delta x tends to 0, dx tends to 0, then it would becomes 0. So therefore we can ignore this portion and then this would be v equals to dm by dx. So we can say that the shear force is nothing but a function with rate of change of moment along x axis. Now we will see the next, that we know that curvature and moment relationship, that curvature is nothing but inverse of the radius of curvature and that is nothing but moment upon ei. So how we get these things? We know that nothing but if this beam deflects, so the deflection, if we say that that is y and that's a function of x, because along x that this would be the maximum deflection, and as we would move this side left side it would decrease and at end it would be 0 deflection. So therefore we can say that function deflection is a function of y of x, we are writing along x. So slope is nothing but dy by dx. So we know that curvature is nothing but rate of change of slope, so d theta by dx. So this would become d2y by dx square. So therefore curvature is inverse of the radius of curvature, that would be d2y by dx square, that is equal to m by ei. So therefore m equals to ei into d2y by dx square. So now we have written q of x is nothing but minus of dv by dx, we got from that equilibrium equations. Then we got v equals to dm by dx, and from the moment curvature relationship m equals to ei d2y by dx square. Now if we substitute m in this equation v, then we will get v equals to ei d3y by dx cube, and then if we substitute v in this equation, we will get q of x equals to minus ei d4y by dx to the power 4. This is the governing differential equations of a beam, fourth order governing differential equations. So now we will just go to the Mathematica software and we will see how we can get the shear force and bending moment diagram from there. So we will just start. So now first of all, we know that the length of the beam, suppose it's given 6000 mm in 6 meters, and the modulus of elasticity, material properties of the beam, 21,000. Then the width of the beam is 400 mm, the h, that is the depth of the beam, equals to 800 mm. The load that is acting is distributed load of minus 25 kN per meter, and then moment of inertia I is given as bh by 12 for a rectangular section we are considering. Then the ei, that is the flexural rigidity we can say, or bending rigidity, that is would be em into ig. Then after that we know that the differential equations for a beam, so we have just seen that differential equations of a beam is ei d4y by dx to the power 4, okay, which is a function of x. Here we have written x1 minus of q, because that is equals to q. When we bring one side of that, then equation will be minus of q, that equals to 0. So this is the differential equation. Now let us start with the first one. Let us just uncomment the section first of all. Yes, so for the simply supported both end, if the beam is simply supported at both end, what we know that, let us see first here, that if the support is simply supported, let us see what will be the case. Both end is simply supported, then what will the boundary conditions for this? The deflection should be 0 here, so y at 0, that should be equals to 0 if we choose x from this side. So y at x equals to 0 should be 0, and if the length of the beam is L, so we can say, and the deflection at y at L, that should also be 0. So the deflection at both end is 0. Now what we know about this hinge supports, that the bending moment is also 0 here. So therefore we can say that the moment at this point x equals to 0, that is also 0, and the bending moment at m equals to L, m at L, that should also be equals to 0. So we can write these boundary conditions in a fashion that y of 0 equals 0, y of L equals 0, m, that is the moment, what we write the moment as ei d2y by dx square. Ei is the material properties, that will be equals to 0, so we can write that d2y by dx square at x equals 0, that is also 0, and then d2y by dx square at x equals to L, that is also 0. So these four boundary conditions we are having here, okay. So four boundary conditions, and it is the fourth order differential equation. So four unknowns will be there. If we integrate these functions, we will get four unknowns, okay. So then we know that four boundary condition is required to get the unit displacements. So we will get after just putting this. So for simply supported case, we have discussed this. Now we can also discuss for the different other boundary conditions. So let's have some different boundary conditions. What is the different boundary conditions? We can say here, suppose the second boundary condition we are taking as fixed beam, okay, or clamped we can say, clamped beam. Okay. So what would be the boundary conditions here? At from, if we choose x from here, so we can say, and the length is L, so y at this position is also equals to 0, y0 equals to 0, and deflection y at L equals to 0. The other boundary condition what we know, that the deflection as well as the slope is also 0 here at the fixed end or a clamped end, because we know that the deflected shape is somehow like this, okay. So here the deflection and slope is both 0. So therefore we can write the first derivative also 0. So y prime of L equals to 0. This y prime derivative defines as dy by dx at 0. So this indicates this. Okay. So the four boundary conditions we are just looking here. Yeah, we can get from here the four boundary conditions. So this will give for the clamped conditions. We will get the results. Now the third one, if we say, let's say the third one is the one end is clamped and other end is free. So at the clamped end, what we know? Suppose x equals to 0 from here, then deflection equals to 0 and the slope is also 0 at 0. But this end, what we can say, because deflection, it would get deflected, so we can't say, and the deflection will be maximum. So what we can say now from this side, we can say that the bending moment and shear force at this position would be 0. If we draw the diagram, so we can understand from there that shear force and bending moment diagram at the free end of a cantilever beam is 0. So therefore, we can say d2y by dx square at x equals to L, that is 0, and shear force, that is d3y by dx cube at x equals to L equals to 0. So then these four boundary conditions is required for this cantilever beam to get the results. Okay. Now the fourth category, we can also say that, okay, if it is propped cantilever beam, suppose one end is fixed and the another end is roller or hinged, then we know that the deflected shape would be somehow like this. Okay, so therefore the deflection and the slope would be 0 at this end, but here the deflection would be 0 but not the slope. So deflection and moment. So we can write the boundary conditions that y at 0 equals to 0, y prime means slope is also 0 here, and here y at L equals to 0, deflection at this point is 0 but not the slope. So we can say the bending moment, because it is a roller support, so moment would be 0. So moment at L would be equals to 0. Okay, so these four cases we have seen here. So we will see in the Mathematica how we can solve this and how we can get the shear force and bending moment diagram and the deflected shape. So let's start. We are just going to start with the simply supported both end. Okay, so the first case. So let's see the first case. So it is given for the deflection, and we know that the shear force is nothing but EI dy 3 times, means d3y by dx cube. It is written in this fashion. Okay, and the bending moment is written EI d2y by dx square. This d denotes the derivatives. So y, function y, deflected function, and it is 2 times, means second order derivative. So we can write in this way in Mathematica, and then we will just plot the functions first for the deflection and then the shear force and bending moment diagram. So now we will just run. So before that, let's just put the kernel, then just we will run this and we will see. Yeah, so we get here, this is the first one, is the plot of the y, means deflected function. So we can see this 0 to 6000 meter is the length of the beam, and throughout the length of the beam the deflected shape is deflection is shown here. So the deflection is here minus 1.2, because it is shown in the mm, 6000 mm, so this is also in mm. So the deflection is total, the maximum deflection at the center is minus 1.2 mm. Minus shown that this is deflecting the downward direction. Okay, so 1.2 mm is the magnitude, that is the maximum deflection almost at this midpoint of the beam. Okay, now we will see the shear force diagram. So here we can see the shear force diagram, that is linearly varying. Okay, so this is the maximum shear force is at both the end. Okay, so almost here the maximum shear force and at this side. Okay, so this is the shear force of the beam, and this is the bending moment diagram. So we can say that it is the bending moment diagram of the beam. Okay, so the maximum almost 1 into 10 to the power 8, somehow larger than that. So this is shown for the simply supported case, that it is positive throughout the length of the beam. The bending moment is positive here shown. Okay, so this case is for the simply supported. Okay, so we have done for the case of simply supported at both ends. But let's now comment it, and we will go to the clamped condition. Now we will see for the clamped case that what will be the case here. So all output deleting, just quit kernel. We will just evaluate the notebook. So we will see now. Let's go. So we can see here the deflection for the clamped case. So both end is clamped, therefore the deflection is 0, as well as we can see the slope is also 0 at the initial stage, because if you take the tangent to it, it would be just parallel to x-axis. Therefore we can say the slope is also 0 at this end, same at this end. Both end is having the slope and the deflection both 0, and we have applied the same boundary conditions, then we get this results. And the deflection here is almost minus 0.20, or somehow a little more than that, so almost 0.25 mm we can say. So we can say here that the deflection in the last simply supported case for the same distributed load and the same materials, we have seen minus 1.2 mm, but here it's reduced to only 0.2 mm or 0.25 mm. So we can see that for the fixed end conditions, the deflection has reduced, and it reduced almost 4 times of that. Now we will see the shear force diagram. So that is the same force is acting on it, therefore the shear force would be the same. And now we will see the bending moment diagram. So we can see here that bending moment is not throughout the length positive, but at this portion it is positive, and at the end of the section of the beam it is negative. Here it is negative and here it is negative, means this is showing that the bending moment is sagging at the middle portion, where almost you can say at a length from 1x equals to 1000 to almost 5000 mm, that is positive bending moment, and at the end of the supports we are getting the negative bending moment. Okay, so therefore we know that in the RCC design, so we put the steels also at the top for the negative moment or tension to carry the load. Okay, so this from this diagram we can get that how we design the steel also in the RCC beam. So these are required for the design purposes. So we have seen the clamped case also, bending moment diagram, shear force diagram, as well as the deflected shape. Now we will see the another case, clamped and free condition. So before that we have to just comment this case. Let's see this. Yes. Yeah. So now just first of all delete all output, then we will run that, and we will see that clamped free conditions means it is a cantilever case. So let's see for the cantilever beam. Yes, so now we can see for the 6000 mm length of the beam, the deflection is showing minus 10, means more than 10 mm. So for the simply supported case we have seen 1.2 mm deflection, and for the fixed beam we have seen 0.25 mm only deflection, but here it is almost 10 mm, means at the free end the maximum deflection is occurring and a large deflection, it is a large deflection we can say for this beam, 10 mm. Okay, so now we can see the shear force diagram also. So this is the shear force. So at the end the shear force is 0 and it is risen to 15,000. So this is the shear force diagram. Then the bending moment diagram you can see here how it's showing. So bending moment would be negative here because the tension would be appearing. So it is shown in this way. That's the bending moment diagram. So when we design for the RCC buildings, we just see that negative moment. So this is the tension side. Therefore, we will provide that steel according to that. So this is the third case we have seen for the clamp free condition, or we can see the cantilever beam. Now we will see the another case for the clamp pin condition. So first of all, let's just delete all output. We will run this. So let us run and let's see. What's the case? Yes. Now we will see that here at this end the slope and deflection both is 0 because it is a fixed end, and here it is hinged end, only deflection would be 0. Okay, and the bending moment would be 0. So we will see when we will see the bending moment diagram that at this end the bending moment would be 0. So here now it is because it is a plot for the deflection. So how it is shown that this deflected shape is shown in this manner. Okay, so this end is fixed and this end is pinned, and the deflection is maximum is 0.5 mm. So it is larger than the fixed feeds or clamp condition, both end clamped, then it was only minus 0.2 mm, but here it is minus 0.5 mm deflection, but less than the simply supported case and the cantilever case. The next one we will see, it is the shear force diagram shown here, and then the bending moment diagram. So we can see that this bending moment is positive in this range, and after this got negative at the fixed end or clamped conditions case. Near the clamped boundary it is negative. Okay, so this shows the bending moment diagram. So we have just seen all the 4 cases of the beam, that how the shear force and bending moment diagram is plotted in Mathematica. Just in a very easy fashion, we have seen that writing the differential equations here and giving the all the 4 boundary conditions. Then we have just written the equations for the shear force and the bending moment, and then we have just written the command to plot deflections here from the length 0 to L, and in similar way the shear force from the length 0 to L, and then the bending moment, and we got these results. So this is very easy and very much handy to understand these things. So we are just ending this. So thank you.